It left home 4 billion years ago. No one sent it orders. No one waited for its return. The civilization that built it had already lived through ice ages, continental drift, the slow cooling of oceans, the rise and fall of every empire that ever called itself eternal. 4 billion years. That is not a metaphor for a long time. That is the actual span of time it takes for a single-celled organism to become a species capable of making a machine, capable of crossing the galaxy. And now crossing back through what was once the outer solar system, the probe passed the ruins of a world it no longer recognized. The sun had become a red giant. It had swollen to a size that swallowed Mercury and Venus whole, and now pressed its bloated edge to the orbit of the Earth. The Earth itself still existed technically. A scorched lump of iron and nickel, stripped of its oceans, stripped of its sky, stripped of the thin blue membrane that had once made it the most important rock in the known universe. Humanity had not died with it. They had retreated to Europa, 100 million of them, living beneath the ice of a moon that itself had only survived because the sun's expansion melted its frozen seas into something briefly habitable. 100 million people, out of the 8 billion who had once stood on this same ground. And as the probe began to transmit 4 billion years of data, 4 billion years of questions asked and partly answered, 4 billion years of traveling through everything the universe had ever made, the humans who received its signal had a single urgent question. Not what did you find? Not was it worth it? Just this, is there anywhere left for us to go? What you are about to watch is not a documentary about space. It is a documentary about what happens when the universe builds something, capable of asking questions about itself, and whether the answers it finds are enough to justify the asking. In the next hour, we are going to travel from a moon with methane rain to a star that has a secret companion, from a machine that can feel a collision that happened before the Earth existed, to a crack in the fabric of space-time that may be running through the universe right now, wriggling at the speed of light older than any star. And at the end of all of it, I want you to feel something specific. Not wonder, not fear. Something harder to name and harder to forget. Subscribe if you want to know what that something is. Because this story begins not with a telescope. It begins with a moon that has rain. Section 1, Titan. The other Earth picture, a lake. Not a metaphor, not a thought experiment. An actual lake water catching the afternoon light reads at the edge, the sound of a small wave finding the shore. You have stood beside one. You know the particular stillness of that moment when you look out and the horizon meets the sky and everything feels briefly unexpectedly large. Now keep that image, the shore, the sand, the waves, and change one thing. The waves are not made of water. They are made of liquid methane. The rain falling from the sky is not water vapor condensed and released. It is ethane and methane cycling through an atmosphere denser than our own. The sand beneath your feet is not silicon and ground shell and ancient coral dust. It is organic compounds that have been falling from that orange sky for 4 billion years. And the sun, if you can find it through the haze, is 10 times smaller and 100 times dimmer than the one you grew up under. It hangs there like something that has almost given up. You are still standing on a shore. The lake still stretches beyond the horizon. The waves still catch whatever light there is. But you are standing on Titan. Titan is Saturn's largest moon, discovered by the Dutch astronomer Christian Huygens in 1655. Using a telescope he built himself because he found the commercially available ones inadequate. It is 50% larger than our own moon. Its atmosphere is denser than Earth's, a pressure on your chest at the surface equal to standing at the bottom of a deep pool. Its temperature is 179 degrees below 0 Celsius, which is cold enough that water ice is as hard and permanent as bedrock, which is exactly what it is. Titan's crust is made of ice. The rock beneath the ice is more conventional. The sky above it is anything but. On January 14, 2005, a small probe named after Huygens himself, not even 3 meters wide, built by the European Space Agency, carried across 7 years of space attached to the side of NASA's Cassini spacecraft. Detached from its parent vehicle, coasted alone for 22 days, and then entered Titan's atmosphere. It fell for 2.5 hours. It opened a parachute. It descended through an orange sky and landed gently on a shoreline near a methane sea, bounced once, slid to a stop. For 90 minutes it transmitted. Then Cassini moved out of range. The signal faded, and the Huygens probe, this small ambassador of a civilization 400 million miles away, remained on Titan's surface undisturbed, where in all likelihood it sits today. 90 minutes of transmission. That is shorter than most movies. That is all we got from the surface of another world. But in those 90 minutes, Huygens showed us something that shattered a quiet assumption we had been carrying for centuries. The assumption that liquid was rare, that the capacity for chemistry in motion, for mixing and dissolving and recombining, for doing the things that living systems do, required a very specific set of circumstances that only Earth had managed to arrange. Titan does not care about that assumption. Not A, but B. Titan is not a world of ice. It is proof that the universe refuses to limit its experiments to the conditions that made us. But Titan is not alone. Below Europa's ice, there is an ocean older than any human word for water. Section 2. The hidden oceans. Titan is not alone. While Huygens was transmitting from its methane shore, Cassini was already photographing a world that may hold more secrets than anything else in the solar system. A world whose surface looks like someone took a perfectly smooth ball of ice and then shattered it from the inside out. Europa, the fourth largest of Jupiter's moons, slightly smaller than our own moon. A world covered entirely by a shell of water ice, not thin ice, not the kind that forms on a lake in November and cracks when you test it, but ice compressed over billions of years to a thickness of more than 100 kilometers. The ice is as hard as granite. It is not going anywhere. But beneath it something moves. Europa's ice shell groans and shifts along lines called lineae, fractures that run for thousands of kilometers across the surface, filled in with darker material from below, refrozen, then fractured again. These are not static structures. They are the surface expression of a liquid ocean in constant slow motion beneath, warmed by the gravitational flexing that Jupiter's immense gravity imposes on the moon as it orbits. A tidal squeezing, billions of years of tidal squeezing that keeps the water liquid in a place where sunlight has not reached in 4 billion years. That ocean contains more liquid water than all of Earth's oceans combined. And Europa does not sit alone in this. Enceladus, a moon of Saturn, only 500 kilometers across, smaller than the state of Arizona, has a subsurface ocean so active that it fires geysers of liquid water directly into space. The plumes shoot up through cracks in the ice and spray material for hundreds of kilometers before it falls back or escapes entirely into Saturn's rings. We do not have to drill to find the ocean on Enceladus. The ocean is already calling out to us. Ganymede and Callisto, two more of Jupiter's moons, almost certainly contain liquid water beneath their surfaces. Even Pluto, the cold, dark, barely a planet world at the edge of the solar system, clinging to scraps of heat from the radioactive decay of ancient elements in its own core, may harbor a subsurface ocean. The solar system, it turns out, is not dry. It is soaked. Not A, but B. The search for life beyond Earth is not a search for another Earth. It is a search for liquid, and liquid in a solar system of 100 moons is the default. But the most extreme thing in our solar system is not an ocean. It is what hides under the clouds of Jupiter. Section 3, metallic hydrogen and the impossible interior. But before we leave the solar system, before we cross the boundary that separates the familiar from the truly alien, there is something inside Jupiter that demands our attention. Something that has no name in everyday language, because everyday language was built to describe a world where this thing does not exist. Imagine holding a balloon filled with hydrogen gas. Ordinary hydrogen, the simplest element. 1 proton and 1 electron. The first thing the universe ever made. You know what hydrogen is. You have burned it in chemistry class. It floats. It is flammable. It is in every normal context a gas. Now compress that balloon, not with your hands, with the weight of a planet. At 4 million times the atmospheric pressure you experience at sea level, which is the kind of pressure that exists deep inside Jupiter, where the gas layers above press down with the combined weight of a world, 14 times more massive than the Earth. Hydrogen stops behaving like a gas. The electrons, which normally orbit their protons in neat little clouds, get squeezed out of their orbits. They become free. They roam. The protons settle into a crystalline lattice. And when electrons roam freely through a lattice of positively charged ions, that is the definition, the precise physical definition of a metal. At 4 million atmospheres, hydrogen becomes metallic. This was predicted by physicists Eugene Wigner and Hilliard Bell Huntington in 1935, when it was still just a theoretical speculation. But Jupiter does not care about our limitations. Jupiter contains more than enough pressure to turn its hydrogen metallic, and because Jupiter is overwhelmingly made of hydrogen, this means that most of Jupiter, in terms of sheer volume, is made of metallic hydrogen. Most of Jupiter is a substance that has no name in any human language that predates physics. NASA's Juno spacecraft, launched in 2011, entirely solar-powered, mapped Jupiter's gravitational field with enough precision to paint a picture of its interior. What it found was this: there is no surface. There is no solid ground beneath the clouds. There is no floor to the atmosphere, no transition point where gas becomes rock. Instead, there is just an infinite gradient temperature and pressure and density increasing continuously downward through layers of gas and liquid and metallic hydrogen, until you reach the core, which is not a rock, but a diffuse region of incredibly hot material, partially dissolved and spread throughout the inner third of the planet. Jupiter has no center you could point to. It has no edge you could stand on. It is just pressure and temperature and the largest storm in the solar system, the Great Red Spot, a hurricane wider than the Earth, running not on sunlight but on Jupiter's own internal heat, a heat generated by the planet slowly contracting under its own gravity. The Great Red Spot has been raging for at least 200 years. It is not the weather, it is Jupiter. Beyond Jupiter lies a boundary, and beyond that boundary, the Sun can no longer protect us. Section 4, the heliosphere, the last bubble. The Sun is not just a light source, it is a shield. Every second the Sun fires a stream of charged particles outward in every direction. Electrons and protons and alpha particles moving at hundreds of kilometers per second, filling the entire solar system with something astronomers call the solar wind. This wind is not metaphorical, it is real. It pushes on the tails of comets, turning them away from the Sun, regardless of which direction the comet is traveling. It is, in the most literal sense, weather that extends from the Sun to a distance of roughly 18 billion kilometers in every direction. At that distance, the solar wind hits something. The interstellar medium, the thin soup of gas dust and magnetic field that fills the space between the stars, pushes back. The wind slows, it becomes turbulent. It mixes with the surrounding environment. And at the outer edge of that mixing zone, the boundary astronomers call the heliopause, the Sun's influence effectively ends. On August 25, 2012, Voyager 1 crossed that boundary. It was the first human-made object ever to do so. Voyager 1 was launched in September 1977, the year that Star Wars was released, the year that the Atari 2600 changed the meaning of the word game. It was launched on a precise trajectory designed to take advantage of a rare alignment of the outer planets, an alignment that only occurs once every 175 years, using the gravitational fields of Jupiter and Saturn as slingshots, stealing a fraction of each planet's orbital momentum to fling itself outward faster than any rocket could have managed alone. 35 years later, it crossed the heliopause. Beyond the heliopause is something different, not just empty or different. The solar wind that fills our solar system is hot but ordered, dominated by the Sun's magnetic field, a bubble of relative protection from the most energetic radiation the galaxy produces. Beyond the heliopause, that protection ends. What replaces it is the interstellar medium, and inside it traveling freely are cosmic rays. In 1912, an Austrian physicist named Victor Hess attached an ionization detector to a hot air balloon and went up. He did this because scientists had noticed for decades that the air at ground levels seemed to be slightly ionized, charged by some form of radiation they could not identify. The prevailing theory was that this radiation came from the Earth itself, so Hess went higher to test the theory. Higher meant less Earth below, which should mean less radiation. He found more radiation, not less, more. With every kilometer of altitude gained, the ionization increased. At 5 kilometers up, performing the experiment during a solar eclipse to eliminate the sun as a source, he measured radiation levels 3 times higher than at sea level. The Earth was not the source. The sun was not the source. The source was somewhere beyond both. The source was the galaxy. Cosmic rays are not rays in the traditional sense. They are particles, mostly protons, some helium nuclei, occasionally something heavier. They travel at fractions of the speed of light, accelerated by the most violent processes the universe produces. Supernova shockwaves, quasar jets, pulsar, winds, the collision of neutron stars. They carry energies so extreme that the most powerful particle accelerators humanity has ever built cannot approach them. And roughly one of them passes through your body every second. Not through your clothes, through your body. Through the cells of your skin and the walls of your intestines and the tissue of your brain and the spiral strands of your DNA. Most of the time, a cosmic ray passes through you the way a bullet passes through fog without effect. But sometimes, not often, but sometimes a cosmic ray strikes a DNA strand, breaks it, leaves a gap that the cell has to repair. If the repair is wrong, the error is passed on. The cell replicates the error. This is how cancer starts. You are not in danger from cosmic rays at sea level, because the Earth's magnetic field deflects most of them, and the atmosphere absorbs the rest. But beyond the heliopause, where even the sun's magnetic field no longer offers its protection, the cosmic ray environment intensifies dramatically. When Voyager 1 crossed the heliopause, its cosmic ray detector showed a sudden unmistakable jump. The galaxy was louder than the solar system. On that probe attached to a spacecraft that has now been traveling for nearly 5 decades, there is a 12-inch gold-plated copper disc. In the summer of 1977, astronomer Carl Sagan was given 6 weeks to assemble a message. A record, something to attach to Voyager 1 before it launched a record of Earth, intended for whoever or whatever might eventually intercept the spacecraft in the depths of interstellar space. He and his collaborators worked frantically. They included sounds: wind, rain, surf, thunder, the sounds of birds and whales and frogs, a greeting in 55 languages, the music of Bach, Beethoven, Louis Armstrong, a pygmy girl's initiation song, brain waves of a woman thinking about her life, the sound of a mother kissing a child. They attached it to the spacecraft. They sent it into the dark. Sagan wrote of that decision, far from home, untouched by these remote events. The voyagers bearing the memories of a world that is no more will fly on. He wrote this in 1977. He was describing something that had not yet happened. He was writing the epitaph of the Earth in advance, the memories of a world that is no more, and doing it not with grief, but with something that looks from a distance of nearly 50 years, remarkably like hope. As though the act of sending the record, the act of refusing to let the universe be the only witness to what we were, was itself enough. The record did not need to arrive anywhere. It just needed to exist, out there, moving. The Oort cloud stretches for 3 light-years in every direction, and beyond it the first star, and between here and there, nothing. Section 5, the great void between stars. The distance between stars is not large the way a mountain is large. It is large the way nothing is large. There is no analogy adequate to it. Every analogy reduces it to something manageable, something the mind can grab and the mind cannot grab it. But let us try anyway, because the failure of the analogy is itself informative. If the sun were a grain of sand, the nearest star, Proxima Centauri, would be another grain of sand 4 kilometers away. Between them nothing, no other grains, no pebbles. Just 4 kilometers of empty air scaled to the size of grains of sand. 4.2 light-years, which is approximately 40 trillion kilometers, which is approximately 10,000 times the diameter of the entire solar system, which is approximately the distance Voyager 1 will cover in 75,000 years at its current speed. This is the void that every proposal for interstellar travel must cross. We live in the local bubble. The local bubble is a cavity in the interstellar medium, a roughly spherical region about 1,000 light-years across, where the density of interstellar gas is roughly 1/6 of what it is in the surrounding galaxy. Something blew this cavity out. Astronomers believe that something was a series of supernovas, 20 or more massive stars exploding in rapid succession over the past 10 to 15 million years, each explosion blasting a shockwave outward, combining to push a bubble in. The interstellar medium, the size of which dwarfs anything you could usefully compare it to. The solar system has been drifting through this bubble for somewhere between 5 and 10 million years. The evidence of those ancient explosions is not theoretical. It is physical. Rare isotopes of iron-60, a radioactive variant with a half-life of 2.6 million years that is almost impossible to produce in any geological process, have been found embedded in the sediment of the ocean floor. They have been found in Antarctic ice cores. The stars that died to make room for us left their ash in the ice at the bottom of the world. Beat between the bubble and the stars between the solar system and any destination that might be worth traveling to, there is a distance that no human has ever crossed and that no human-made object will cross during any human lifetime currently being lived. And knowing this genuinely, knowing it not as an abstraction but as a felt physical reality, changes something. It changes what the Voyager record means. It changes what Carl Sagan was doing when he wrote that epitaph. He was not writing about the future of space travel. He was writing about the future of memory, about the fact that even if we never leave this solar system, even if we are, in the most practical sense, trapped here, something of what we were can still travel. Not fast enough to matter to anyone living, not addressed to anyone specific, not even likely to arrive anywhere at all. But moving, still moving, always moving. But eventually the void ends. Eventually there is a star. And the universe has been spending the past 10 billion years building the strangest possible kinds of stars. Section 6, Algol the Demon Star. 3,200 years ago, an Egyptian astronomer compiled a list. Not a list of fixed stars, not a list of constellations or planets or the signs of the zodiac. This list was a calendar of lucky and unlucky days, an attempt to predict, based on the behavior of the sky, when fortune would favor and when it would punish. And on certain nights on a schedule too regular to be coincidence, a particular star was marked as unlucky, malevolent. Something to be watched. The star was not doing anything obviously strange. It did not flare. It did not change color. It simply dimmed periodically on a schedule so precise that the Egyptians had noticed it. They named it unlucky because they did not know why it changed. And not knowing why was enough to make them afraid. The Greeks called it the head of Medusa, the severed head carried by Perseus, the most dangerous part of the most dangerous monster, still terrible even in death. In Chinese astronomy, it was associated with a mound of accumulated corpses. Its more common name comes from the Arabic al-Ghul, the demon. The ghoul, the thing that rises from graves to consume the living. In the language of modern astronomy, it is Beta Persei, the second brightest star in the constellation Perseus, 90 light-years from Earth, and it dims every 2.87 days. This was not explained until 1783, when an 18-year-old amateur astronomer named John Goodricke, deaf from birth, who died at the age of 21, 2 weeks after being elected to the Royal Society, measured Algol's brightness variations with enough precision to propose that a dark companion was periodically crossing in front of the brighter star, blocking its light as seen from Earth. He was right. He died before anyone confirmed it, but he was right. There are two stars in the Algol system, one bright, one dim. They orbit each other every 2.87 days. And when the dim companion passes between the bright star and the Earth, Algol dims. So far, so elegant. But here is where Algol becomes genuinely disturbing. The two stars in the Algol system were born at the same time from the same cloud of gas and dust as twins. And in stellar physics, larger stars burn faster. So the larger star should be older, more evolved further along in its life cycle, closer to death. And yet, when astronomers measure the two stars, they find the opposite. The smaller, dimmer companion is the older star. It is already a subgiant, bloated and used up. The larger, brighter primary is still in the prime of its hydrogen-burning life. This makes no sense. Unless at some point in the past, the companion star reached the end of its main sequence life and expanded into a red giant. And as it expanded, it overflowed the gravitational boundary between itself and its companion. Its outer layers, its hydrogen envelope, the fuel it had been saving for its old age, spilled across the gap between the two stars, and the companion drank it. In the language of astrophysics, this is called mass transfer. In any other language, it is a star stealing the life of its sibling. The companion consumed so much of Algol's hydrogen that it effectively reversed. The aging process of the primary, the big star fed, grew massive and bright, and now burns young and vigorous, while the donor star it drained hangs beside it, shrunken and exhausted. The demon star has a victim, and this thing that the Egyptians marked as unlucky, that the Greeks made into a severed head, that a deaf 18-year-old measured in his garden, turns out to be one of the most common things in the galaxy. More than half of all the stars in the Milky Way exist in binary or multiple systems. We look up at the night sky and see individual stars, each one isolated in its brightness. Most of them are not alone. Most of them carry companions we cannot see without instruments. But the sky also contains stars so massive that nothing in daily human experience provides any useful comparison. Stars that do not merely burn, they boil and convulse and change and surprise us in ways we are only now beginning to understand. Section 7. Betelgeuse the star. That has a secret. In the winter of 2019, something happened to Betelgeuse. It dimmed, not subtly, dramatically, by more than 40% over a period of weeks. A star that had been one of the 10 brightest objects in the night sky fell to something like 21st place. Astronomers around the world pointed their instruments at it. Social media lit up with a phrase that no one had typed with genuine urgency in living memory: Betelgeuse might be about to explode. It was not about to explode. What happened was, in retrospect, both simpler and stranger than an impending supernova. Betelgeuse had ejected a mass of superheated plasma from its surface, not unusual for a star of its type. But as that plasma traveled away from the star, it cooled. And as it cooled, it condensed into dust. And the dust formed a cloud, and the cloud moved between the star and Earth. And for several weeks, Betelgeuse was partially obscured by its own expelled material. Then the cloud dispersed. Betelgeuse brightened again. But the instruments that had been trained on Betelgeuse did not stop. And two research teams working independently noticed something in the data: a pattern of brightness variation over a roughly 6-year cycle that did not match any known mechanism of stellar pulsation. The teams modeled the data and arrived at the same conclusion: there was likely a companion. In July 2025, a team led by Steve Howell at NASA's Ames Research Center confirmed it. They used an instrument called the Alupeke Speckle Imager, mounted on the Gemini North Telescope on the summit of Mauna Kea in Hawaii. With it, Howell's team found what had been suspected and never confirmed: a second star orbiting Betelgeuse. They named it Siwarha. The name comes from the Arabic for her bracelet, a companion circling Betelgeuse the way a bracelet circles a wrist, in honor of the Arabic root of Betelgeuse's own name, which most scholars translate as the hand of the giant, referring to Orion. The hand has a bracelet, Siwarha. Siwarha is not large, approximately 1.5 times the mass of the Sun, a young blue-white star that may not yet have ignited hydrogen fusion in its core. It orbits Betelgeuse at a distance of roughly 4 astronomical units, 4 times the Earth-Sun distance. And Betelgeuse is nearly 700 times the diameter of the Sun, which means Siwara is not merely near Betelgeuse. Siwara is inside Betelgeuse's outer atmosphere. It orbits within the extended envelope of plasma that the supergiant continuously sheds. It is a star inside another star's atmosphere. Within roughly 10,000 years, Siwara's orbit will decay. The tidal forces between the two stars will pull them together, and the smaller star will spiral into Betelgeuse and be consumed. That collision will almost certainly destabilize the supergiant further. It may accelerate the very supernova it would otherwise have postponed. Betelgeuse is going to end. We just don't know when. And when it does, when the star finally runs out of silicon in its core and iron begins to accumulate and nothing remains to stop the core from collapsing, the explosion will be visible in daylight. It will be as bright as the half moon, which means it will cast shadows at night. It will be uncomfortable to look at directly. It will last for weeks, maybe months before fading. And when it fades, the constellation of Orion, the hunter who has stood in the winter sky since before any human wrote down what they saw, will stand in the sky without his shoulder. Not A, but B. Betelgeuse is not a tragedy in progress. It is a promise the universe made before it knew we would be here to watch it keep. But the most important star for life is not Betelgeuse. It is the smallest one, the one our nearest neighbor orbits. Section 8. Proxima Centauri and the Ribbon World. At 4.2 light years from Earth, the nearest star to the solar system, there is a red dwarf. Red dwarfs are the most numerous type of star in the galaxy. They contain somewhere between 7 and 50% of the Sun's mass, which means they burn their hydrogen much more slowly, which means they live much longer. While a star like the Sun will burn for roughly 10 billion years before expanding into a red giant, a small red dwarf might burn steadily for 10 trillion years. The current age of the universe is 13.8 billion years. No red dwarf has ever come close to dying. The universe is not old enough yet for any red dwarf to have reached old age. Proxima Centauri is a red dwarf, and it is our closest neighbor, and it has a planet. Proxima b, the first and so far most studied of potentially several planets orbiting Proxima Centauri, is a rocky world roughly the mass of the Earth orbiting within the star's habitable zone. Proxima b orbits at approximately 1/20th the distance that the Earth orbits the Sun. A year on Proxima b lasts about 11 Earth days. At that distance, the gravitational tide the star exerts on the planet is so strong that the planet almost certainly no longer rotates freely. It has been pulled into what astronomers call tidal lock. One face of the planet permanently points toward the star. One face permanently points away. On the star-facing side, it is always noon. On the far side, it is always night. There is no sunrise on Proxima b. There is no sunset. The sun Proxima Centauri, red and enormous in the sky, simply hangs. Fixed, it has never moved. It will never move. On one half of the world, it has been noon since the planet formed. On the other half, it has been midnight. Between those two extremes in the thin strip that runs around the planet's equator, in the twilight zone between eternal day and eternal night in the Terminator region, there might be a balance. The star side is too hot, the night side is too cold. But in the ribbon, the narrow band where heat from the day side and cold from the night side meet temperatures might be stable. If life exists on Proxima b, it lives on a ribbon, a thin strip of acceptable conditions on a world otherwise committed to extremes. Sound familiar? Red dwarf stars are also violent. They flare. They produce sudden massive eruptions of electromagnetic radiation, ultraviolet and X-rays and charged particles that would, if Proxima b has no magnetic field strong enough to deflect them, strip its atmosphere from it over geological time. But here is what we know with certainty. Proxima Centauri, this dim, violent, patient red star, will still be burning when the sun is dead. It will still be burning when the galaxy has changed beyond recognition, long after Betelgeuse has exploded and Siwara has been consumed and the Milky Way has merged with Andromeda Proxima Centauri will still be fusing hydrogen in its small, conservative, unhurried core. The nearest star is the most patient thing we know. But patience is not available to the most massive stars. And for most of the stars in the galaxy, the ones that were born large and burned fast and ended violently, the end is not a gentle dimming. The end is something that in a very specific and chemically verifiable sense, we owe our existence to entirely. Section 9, the B² FH paper, where everything comes from. In 1957, at Cambridge University, 4 people wrote a paper that changed what we understand ourselves to be made of. Their names were Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. The paper is known by their initials B² FH. It explained something that had been unexplained for decades, something so fundamental that its absence from the literature represented an enormous gap in humanity's understanding of itself. The paper explained where the elements come from. Not hydrogen. Hydrogen was created in the Big Bang in the first few minutes of the universe's existence, when a soup of quarks and gluons condensed into protons and neutrons, and those protons and neutrons fused briefly into helium and a scattering of lithium before the universe cooled too much for fusion to continue. The problem was everything else: carbon, oxygen, nitrogen, iron, gold, the calcium in your bones, the iron in your blood, the phosphorus in your DNA, the silicon in every computer ever made, the oxygen in every breath you have ever taken. None of these were created in the Big Bang. They did not exist when the universe was young. Where did they come from? B²FH answered from stars. When a star like the Sun burns through its hydrogen, it leaves behind helium ash in the core. When the core gets hot enough, the helium ignites, and helium fusion produces carbon and oxygen. When a more massive star burns through its carbon, it produces neon and magnesium. Through oxygen, it produces silicon and sulfur. Through silicon, in a burst of fusion that lasts only hours, it produces iron. At iron, the story ends. Iron is the most stable nucleus in the universe. Fusing iron does not release energy, it absorbs it. And so when the core of a massive star fills with iron, there is nothing left to push back against the gravity pressing in from all sides. The energy source fails, the fusion stops, and the core collapses. What follows is one of the most violent events the universe produces. The iron core, a mass approximately equal to the Sun, compressed into a sphere roughly 30 kilometers across, collapses to something roughly 20 kilometers across in less than a second. The density becomes so extreme that the electrons and protons in the iron atoms are forced together, merging to form neutrons. The core becomes, in essence, a single enormous atomic nucleus, and then the infalling material of the outer star hits. That core hits it at a substantial fraction of the speed of light and bounces. The shock wave propagates outward. It passes through the star's outer layers, blasting them into space at velocities approaching 10% of the speed of light. In the nuclear cauldron of that shock wave, elements heavier than iron are forged. The elements that are literally impossible without this precise mechanism of stellar death. Gold, uranium, lead, mercury, iodine, all of them created in the seconds of a supernova explosion and thrown across the galaxy. A supernova outshines its entire host galaxy. For a brief period, a single dying star produces more light than 100 billion stars combined. Margaret Burbidge was in 1954 turned down for a fellowship to use the Mount Wilson Observatory, one of the most powerful telescopes in the world at the time, because the observatory had only one toilet on site, and that toilet was for men. The fellowship went to her husband Geoffrey instead. Margaret went along as his assistant. The authorities looked the other way. She used her husband's telescope access to co-write the paper that explained how the universe makes everything that exists. She later became the first woman director of the Royal Greenwich Observatory. She was offered the American Astronomical Society's Annie Jump Cannon Award, an award specifically for women in astronomy, and declined it on the grounds that having a separate award for women was patronizing. She wanted the same award as everyone else. She wanted to be evaluated on the same terms. She was right, not A but B. The iron in your blood is not a coincidence of chemistry. It is the legacy of a star that died before the Earth existed, that burned through hydrogen and helium and carbon and silicon in a sequence spanning millions of years, then collapsed and exploded and scattered its core across the galaxy. You carry the obituary of a dead star in every red blood cell in your body. But it is the deaths of the most massive stars that give the universe its most extreme objects. Section 10. Neutron stars, nuclear pasta, and cosmic lighthouses. When the core of a massive star collapses, one of two things happens. If the core's mass falls below a certain limit, roughly 2 to 3 times the mass of the Sun, the collapse stops. The neutrons themselves resist further compression, supported by quantum mechanical forces that prevent any two neutrons from occupying the same quantum state simultaneously. The core becomes a neutron star, a sphere roughly 20 kilometers across, containing more mass than the Sun, sitting in the expanding cloud of the supernova that created it. 20 kilometers across. If the island of Manhattan were compressed to the density of a neutron star, it would fit inside a period at the end of this sentence. A teaspoon of neutron star material would weigh approximately 10 million tons. The gravity at the surface is 100 billion times stronger than on Earth. But the surface is not the strangest part. Inside a neutron star under pressures that no laboratory on Earth can reproduce, and no theory has fully described, the neutrons organize themselves into structures. At certain depths, the neutrons form long, thin tubes, strands running parallel to each other through the nuclear material. At other depths, they form flat sheets. At others, they form perforated slabs with cylindrical holes running through them. Astrophysicists, in a moment of nomenclatural whimsy that has survived into the formal literature, named these structures after pasta. The interiors of neutron stars are made of nuclear spaghetti, nuclear penny, nuclear lasagna. These are not colloquial terms. They are in the peer-reviewed literature. The strongest known material in the universe, the material that makes up the crust of neutron stars, is nuclear pasta with a shear modulus approximately 10 billion times stronger than steel. This is what remains when a star dies. In September 1967, a 24-year-old graduate student at Cambridge named Jocelyn Bell was manually reviewing paper printouts from a radio telescope. She had spent years helping to build the telescope literally with her own hands, hammering stakes into the ground in the English countryside, and now she was its primary operator, monitoring its output night after night looking for quasars. She found something else. A brief regular pulse of radio emission repeating every 1.337 seconds. Not approximately exactly, with a precision exceeding that of the most accurate clocks available in 1967. She noted it. She came back. It appeared again in the same part of the sky at the same interval. She named it LGM1, Little Green Men. She was not entirely joking. Nothing natural that astronomers knew about in 1967 could produce such a regular, rapid pulse. The only explanation that seemed to fit was something artificial, something engineered. It was not engineered. It was a neutron star. Neutron stars spin rapidly, much more rapidly than the larger stars they were compressed from, for the same reason that a figure skater spins faster when they pull in their arms. They also carry magnetic fields compressed and intensified by the collapse to magnitudes billions of times stronger than the Sun's. And those magnetic fields, combined with the rotation, generate intense beams of radio emission from the magnetic poles, sweeping the beam around as the star rotates like the beam from a lighthouse. If the Earth lies in the path of that sweep, we detect a pulse. A pulsar. The fastest known pulsar rotates 716 times per second. That is 43,000 revolutions per minute. Faster than any jet engine, faster than any mechanical object humanity has ever built. A dead star smaller than a city spinning faster than our fastest machines. And for discovering this, Jocelyn Bell's supervisor, Anthony Hewish, was awarded the Nobel Prize in Physics in 1974. Bell received nothing. She has said in interviews that she does not resent this, that she understands the Nobel Committee's reasoning. She was made a Dame of the British Empire. She has received honours and awards and honorary degrees from universities around the world. She did not receive the Nobel Prize for discovering the most precisely timed natural objects in the universe. The universe does not balance its ledger fairly. We knew this already, but it is worth repeating. Not all neutron stars are merely fast spinning. Some are something else, something so extreme that the word extreme loses meaning. A magnetar is a neutron star with a magnetic field roughly 1 quadrillion times stronger than the Earth's. 1 quadrillion is a 1 followed by 15 zeros. At that field strength, the magnetic field would be powerful enough to polarize the vacuum of space itself. It would distort the electron orbits in every atom in your body. The atoms in your body would be stretched into thin needles aligned with the field lines, elongated to 100 times their normal size. All chemical bonds, the bonds that hold your molecules together, that hold your cells together, that hold your thoughts together, rupturing instantly. You would not merely die. You would become something other than a collection of molecules before you finish dying. A magnetar within 1,000 light-years of Earth would strip the oxygen from our atmosphere before we finished writing the sentence to describe what was happening. None are that close at the moment. But neutron stars are only one possible outcome of a massive stellar collapse. If the core mass exceeds the limit that neutron degeneracy pressure can support, the collapse does not stop. And what that produces is not a new kind of star. It is something for which we have no adequate language. Section 11. Black holes where the universe runs out of rules. In December 1915, a German physicist named Karl Schwarzschild was serving on the Russian front of the First World War. He was 41 years old. He had volunteered despite being well past the age of conscription. He was by any reasonable measure somewhere he should not have been, a mathematician and astronomer in a trench while the world was trying to kill itself. And while he was there, he read Albert Einstein's new theory of general relativity published that November. And in the time between artillery barrages in whatever quiet he could find, in one of the most violent theaters of the most violent war in history, to that point, he found the first exact solution to Einstein's field equations. He wrote the solution in a letter to Einstein. The letter began, "As you will see, the war is kindly disposed towards me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this your land of ideas." He sent the letter. Einstein presented the solution to the Prussian Academy of Sciences, and Karl Schwarzschild died less than 6 months later in May 1916 of an illness he contracted at the front. He never knew what his solution implied. What it implied was this: if mass is compressed into a small enough volume, the curvature of space-time around it becomes so extreme that not even light can escape. There is a critical radius, the Schwarzschild radius below, which, if you compress any amount of mass, the gravity becomes infinite and light cannot leave. This boundary is what we now call the event horizon, and the object within it is what we now call a black hole. Einstein did not believe black holes were real. He published a paper in 1939 specifically arguing that they could not form in nature. Most of the physics community agreed with him. In 1975, Stephen Hawking and Kip Thorne made a bet. Both had spent significant portions of their careers studying black holes. Hawking wagered that the X-ray source Cygnus X1 was not a black hole. The bet was structured as a kind of consolation prize if black holes turned out not to exist. Both physicists would be out of a job, but at least Hawking would win a magazine subscription. If they were real, he owed Thorne a subscription to Penthouse. By 1988, Hawking had conceded the bet. On September 14, 2015, at 5:51 in the morning Eastern Time, a ripple passed through the LIGO detector in Livingston, Louisiana. 4 milliseconds later, a second ripple passed through the LIGO detector in Hanford, Washington. LIGO, the Laser Interferometer, Gravitational Wave Observatory, is a machine designed to measure changes in distance using lasers and mirrors. Its 2 arms are each 4 kilometers long, and the light bouncing between. Their mirrors can detect changes in length as small as 1/10,000th the width of a proton. To make that concrete, LIGO can measure a change in length equivalent to the width of a human hair across the distance to Proxima Centauri, 4 light-years. That is the sensitivity required to detect what the universe produces. What passed through LIGO on September 14, 2015, was a gravitational wave. A wave in space-time itself, compressing and stretching the very geometry of the universe as it passed. The wave was produced by 2 black holes, each approximately 30 solar masses, which had been spiraling toward each other for billions of years. They had begun their final approach before the Earth existed, and which had approximately 1.3 billion years ago merged. The energy released in that merger, equivalent to the complete conversion of 3 solar masses into pure gravitational radiation, rippled outward. For 1.3 billion years, the ripple traveled through the universe. Then it hit LIGO. The instrument moved by 1/10,000th the width of a proton. We felt it. We built a machine so precise, so astonishingly improbably precise, that we could detect a collision that happened before complex life existed on Earth, at a distance of 1.3 billion light-years, producing a distortion in space-time that moved our mirrors by a fraction of the width of a subatomic particle. There is no adequate word for this. The word achievement is insufficient. The word miracle is technically wrong, but emotionally accurate. What we did with LIGO is something that should not, by any reasonable measure of what a small, fragile, biologically limited species can accomplish, have been possible. We did it anyway. At the center of the Milky Way, 26,000 light-years from Earth, there is a black hole with the mass of 4 million suns. It is called Sagittarius A star. Its event horizon has a radius of roughly 44 million kilometers. If it were placed at the center of our solar system, it would extend past the orbit of Mercury, consuming the planet entirely. The stars that orbit it reach speeds of 30% of the speed of light as they whip around their closest approach. 2 astronomers, Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute, spent decades mapping those orbits. They produced the first precise measurement of Sagittarius A star's mass. For this, they shared the 2020 Nobel Prize in Physics. In 2022, the Event Horizon Telescope, a collaboration of radio telescopes spanning the entire planet, combined into a single instrument, the diameter of the Earth, produced the first direct image of Sagittarius A star itself. Not an artist's impression, not a simulation. A photograph, a ring of glowing plasma surrounding a region of absolute darkness, the shadow of an event horizon. We photographed a black hole. Inside the event horizon of a black hole, something happens that no theory we have can describe. General relativity predicts a singularity, a point of infinite density at the center of every black hole, where the equations produce nonsensical results, where our understanding of reality literally breaks down. Quantum mechanics predict something different, but equally unresolvable. The 2 theories, the 2 most tested, most precise, most predictively successful theories in the history of science, give incompatible answers when applied to the interior of a black hole. The reconciliation of general relativity and quantum mechanics is the central unsolved problem of modern physics. The answer, whatever it is hidden inside every black hole, and the only way to access it is to cross the event horizon, from which nothing, not information, not matter, not light, returns. We can observe, we cannot enter. We can know the shape, but not the secret. Not A, but B. A black hole is not a hole. It is a place where the universe ran out of rules and kept going anyway. And the only way to find out what happens next is to go somewhere you can never come back from. But Sagittarius A star is quiet. Somewhere in the universe, in many places in the universe, there are black holes that are not quiet at all. Section 12. Quasars, the most violent thing in the universe. In 1933, a 22-year-old named Grote Reber applied for a job at Bell Laboratories. He was rejected. Rather than consider other options, he went home and built a radio telescope in his backyard in Wheaton, Illinois. He completed it in 1937. For the next several years, he was the only radio astronomer in the world. The only person on Earth operating a radio telescope, the only person listening to the sky in wavelengths that no human eye could perceive. He created the first radio maps of the Milky Way. He found sources of radio emission that no one had noticed before. One of those sources, a particularly intense emitter in a distant galaxy, would eventually be understood as something that should not exist. An object the size of a solar system producing more light than 1,000 galaxies combined. At the center of most large galaxies, there is a supermassive black hole, and some of those black holes are actively feeding, consuming surrounding material at rates so extreme that the accretion disk around them heats to temperatures of quadrillions of degrees. As material falls inward, it compresses and radiates. X-rays, ultraviolet light, visible light, radio waves, all of it simultaneously, all of it from a structure not much wider than the orbit of Pluto. This is what a quasar is, not a star, not a galaxy. A supermassive black hole eating, and the light of its eating outshining everything around it. The most distant known quasar UHZ, one discovered in 2023, sits 13.2 billion light-years away, meaning we see it as it was when the universe was less than 5% of its current age. It was already consuming material at quasar rates when the universe was young. The reason quasars are so distant is that quasars are a feature of the young universe. They represent a phase in the life of large black holes, a period of intense growth that requires a supply of cold gas to feed the black hole at the required rate. Over time, the gas runs out. The quasars go quiet. Sagittarius A star went quiet. This was for the living things on Earth a matter of survival. An active quasar at the center of the Milky Way, at a distance of 26,000 light-years, would not merely be visible from Earth. It would be lethal. The radiation would strip our atmosphere. It would break down the ozone layer. It would bathe the surface of the Earth in X-rays and ultraviolet radiation intense enough to destroy complex organic molecules. We exist because our galaxy's central black hole fell quiet before we evolved. We have always been one sleeping giant away from nothing. But even quasars are not the universe's deepest strangeness. The true architecture of the universe is something else entirely. Section 13. The Cosmic Web and the Void. Look at a map of Paris from above. The streets radiate from the center. They converge on monuments and plazas. And beneath the southern part of the city, beneath almost the entire right bank, there is an emptiness, a vast network of tunnels quarried for limestone over centuries, that underlies the city's stone buildings and stone streets and stone monuments like a shadow cast downward into the earth. Paris is built on nothing. The limestone that gives the city its uniform pale beauty was pulled out of those tunnels over hundreds of years. The underground was depleted so thoroughly that buildings began to collapse into the voids, and the city moved its dead 6 million of them into the tunnels to stabilize the ground. The catacombs of Paris are the negative space that the city required in order to exist. The grandeur above is a consequence of the emptiness below. The universe is built on exactly this principle. In 1978, two astronomers named Robert Kirshner and Stephen Gregory were mapping a region of the sky in the constellation Bootes. They were looking for a filament of galaxies. What they found instead was that where the galaxies should have been, there were almost none. A region hundreds of millions of light-years across that contained perhaps 60 known galaxies where standard cosmological models predicted thousands. Their colleagues told them their survey was incomplete. They were not wrong to be skeptical. The idea that the universe contained regions of that size that were genuinely empty, not just sparsely populated, but effectively empty in a way that challenged the assumption that matter was broadly distributed throughout space, was difficult to accept. The Bootes void is real. It is roughly 330 million light-years across. It contains 60 known galaxies. It should contain tens of thousands. Its nearest edge is approximately 500 million light-years from Earth. This is not far by the standards of what we have been discussing. This is our neighborhood. Our own supercluster, discovered and named by astronomer Brent Tully in 2014, is called Laniakea. In Hawaiian, this means immeasurable heaven. It contains more than 100,000 individual galaxies. It stretches 500 million light-years across. It is itself one branch of a larger structure connected to other superclusters in a web that spans the entire observable universe. The cosmic web is not a metaphor. It is a real physical structure confirmed by three-dimensional surveys of millions of galaxies, produced by the earliest fluctuations in density from the Big Bang, microscopic variations, quantum fluctuations blown to cosmological scale by inflation, which over 13 billion years of gravitational growth became everything we can see. The voids were not always there. They were once subtle low-density regions. Over billions of years, the gravity of the denser regions drained the voids. Material that once filled them flowed slowly toward the filaments and walls and clusters. The voids gave their substance to make the grandeur of the cosmic web. The emptiness is not a failure of the universe. It is the engine of its structure. In 2024, the Dark Energy Spectroscopic Instrument DESI completed the most precise three-dimensional map of the universe ever made. 6 million galaxies, 11 billion years of cosmic history, and the data suggested something troubling. Dark energy, the force accelerating the universe's expansion, may not be constant. It may be evolving. The universe may be changing its mind about how fast it wants to expand. We have mapped 6 million galaxies across 11 billion years, and after all of that, the universe looked back at us and said not quite. But the deepest mystery in the universe is not in the emptiness between galaxies. It is in the structure of space-time itself, in the wounds that creation left behind. Section 14. The Scars of Creation. There is a shirt in your closet, or wherever you keep your shirts, that has a wrinkle in it. You can feel the wrinkle. You can see it. But if you ask what the wrinkle is made of, the answer is nothing. The wrinkle is not a substance added to the shirt. It is not a feature of the fabric's weave. It is just the shirt arranged in an uncomfortable way. The wrinkle has no material content. It is a topological accident, a consequence of the way the shirt was folded or stored or pressed. And it holds a certain amount of energy, the energy required to smooth it out. That energy is real, even though the wrinkle itself is nothing. Scale this up, not to the size of a room, not to the size of a planet, not to the size of a galaxy. Scale it up to the size of the entire observable universe, and make it not a wrinkle in fabric, but a wrinkle in space-time itself, in the fundamental geometry of existence, and you have a cosmic string. Beat in December 1979, a physicist named Alan Guth spent the night working through a problem that had been bothering him for years. He had been trying to understand why the universe was so geometrically flat, why parallel beams of light remained parallel across billions of light-years, and why the cosmic microwave background was so uniform in temperature from one end of the observable universe to the other, even though regions that far apart could never have been in causal contact during the early universe. That night at his office at Stanford, he found an answer. The universe had inflated in the first 10 to the minus 32nd seconds of its existence, a time interval so short that there is no human experience or analogy to place it against. The universe had expanded by a factor of at least 10 to the 50th power. Every point in space had been pushed away from every other point faster than light could travel between them. This inflation explained the flatness. It explained the uniformity. And Guth recognized immediately what he had found. He drew a box around his notes and wrote in capital letters, "Spectacular Realization." That notebook is now on permanent display at the Adler Planetarium in Chicago. But inflation created a problem. The early universe was not smooth. It was an environment of almost incomprehensible energy, in which the forces of nature were not yet separated, in which gravity, electromagnetism, and the nuclear forces were unified into a single force. The way water is a single substance before you freeze it and it becomes ice, with all of its facets and grain boundaries and structural irregularities. As the universe expanded and cooled, the forces separated from each other. Symmetry-breaking physicists call it in a series of phase transitions. Each transition was a phase change, like water freezing into ice, and like any phase change, it was not perfect. When water freezes, the ice that forms has grain boundaries, lines where two regions of crystallizing ice growing from different nucleation points meet each other. The boundary is not made of anything special. It is just the geometry of the crystal arranged wrong. When space-time froze, when the forces separated and the universe became what it is, the same thing happened. In some models of the physics of that era, the universe formed defects. Topological defects, not objects in the conventional sense, but permanent mismatches in the geometry of space-time, fixed in place by the mathematics of the phase transition. Cosmic strings are one type of defect. They are one-dimensional objects infinitely thin, or as close to it as physics allows, with a width smaller than a proton. But their length is measured in light years. In the most extreme estimates, a single cosmic string might stretch across the entire observable universe 93 billion light-years from one end to the other. The mass of that string, the energy locked up in its geometric defect, is approximately 10 billion tons per centimeter of length. A kilometer of cosmic string would outweigh the entire Earth. Not because it is made of anything dense, it is made of nothing. It is a wrinkle in space-time, and wrinkles carry energy, and energy has mass. If a cosmic string passed through the Earth, it would not stop. It would slice through our planet as though we were not there, because to a defect in space-time, we are barely a footnote. In June 2023, 4 independent teams of astronomers simultaneously published papers presenting evidence for something called the gravitational wave background. Not a specific gravitational wave event like the merging black holes that LIGO detected in 2015, but a constant, pervasive, low-frequency hum of gravitational waves, a background noise in the fabric of space-time itself, coming from every direction simultaneously. The most likely explanation is a background of gravitational waves from thousands of pairs of spiraling supermassive black holes too far away and too slow to detect individually. But the data does not rule out a different source. One of the candidate sources is cosmic strings. When a cosmic string loops back on itself and forms a closed loop, the loop vibrates. It shrinks, it radiates gravitational waves, and then it disappears, converting itself entirely into a burst of gravitational radiation. This process, happening repeatedly all over the universe for billions of years, would produce exactly the kind of low-frequency gravitational wave background that the pulsar timing arrays detected. The hum that fills the universe might be the sound of the universe's oldest wounds healing. And then there is this. In May 2025, the James Webb Space Telescope confirmed the most distant galaxy ever detected. It is called MOM-Z14. Its light reaching us now, after traveling for nearly the entire age of the universe, was emitted just 280 million years after the Big Bang. The universe at that moment was approximately 2% of its current age. And that galaxy does not match the models. It is brighter than it should be. Its chemistry is wrong. It contains an overabundance of nitrogen that no theoretical framework can fully explain. It formed too quickly in ways that the standard story of how galaxies grow cannot accommodate. The researchers wrote, there is a growing chasm between theory and observation related to the early universe. Maybe MOM-Z14 is an anomaly. Or maybe the early universe was shaped by things we have not yet accounted for, things whose gravitational influence during the era when galaxies were first forming could have accelerated the collapse of gas into structures seeding galaxy formation before the standard models expect it to begin. We do not know. We do not know if cosmic strings exist. We do not know what space-time looks like where a cosmic string passes through it. We do not know what would happen if a cosmic string intersected with another cosmic string, and both of them broke and reformed in new configurations, releasing energy at the speed of light into the surrounding universe. We do not know if the low-frequency hum that fills the universe, the gravitational wave background that 4 independent teams of astronomers detected in 2023, is the death rattle of loops of cosmic string vibrating themselves out of existence. We do not know if MOM-Z14, the oldest galaxy we have ever seen, formed the way it formed because a cosmic string seeded its formation in the first moments after the Big Bang. We do not know what the universe looked like at 10 to the minus 30 seconds when inflation ended and the forces separated and the geometry of space-time settled into whatever form it took with whatever defects it carried. We do not know if those defects persist, but we know this. The universe was once so hot, so violent, so barely past nothing, that the forces of nature were still negotiating what they wanted to be. The rules of physics were not yet fixed. The geometry of space was not yet settled. And whatever emerged from that negotiation, whatever permanent structures, the phase transitions left behind in the fabric of everything, those structures are older than any star, older than any galaxy, older than any element, heavier than hydrogen. If they exist, they are still out there, wriggling at the speed of light, bearing the memory of a universe that no longer exists. The transmission 4 billion years after it was launched, the probe found its way back to a solar system that had not waited for it. The sun was dying. Mercury and Venus were already gone, swallowed by the expanding red giant that had once given them light. Earth was a ruin, scorched and stripped, reduced to its iron-nickel core by 10 billion years of stellar evolution. And humanity, 100 million of them, in the ice-warmed oceans of Europa, the last habitable moon in a solar system, running out of time, received the probe's transmission. For weeks they listened. The probe had traveled through the metallic hydrogen core of Jupiter. It had recorded the plumes of Enceladus and measured the depth of Europa's hidden ocean. It had passed through the heliopause and listened to the gravitational music of the galaxy through an antenna 1,000 kilometers long. It had watched the Algol system slowly reverse its own aging through mass transfer. It had tracked Betelgeuse as Siwara spiraled inward. It had flown close enough to Proxima Centauri to measure the magnetic field of Proxima b. It had observed the collapse of neutron stars. It had photographed the jets of quasars. It had mapped the Bootes void and found that the Bootes void was emptier than the models predicted even for emptiness. It had found in the gravitational signal of a pulsar timing array it constructed, from a network of dead stars across the Scutum Centaurus arm, the faint signature of a gravitational wave background. And in the heart of the Bootes void, drawn by an anomalous clustering of gravitational wave data, guided by coordinates reconstructed from the trajectories of particles, accelerated to energies beyond anything in our physics, it had found something. Not a galaxy, not a star, not a planet, a line, barely detectable, splitting the light from the background galaxies it passed in front of, gravitationally lensing everything around it with the precise signature of a one-dimensional mass. A cosmic string. The probe could not touch it, could not measure it directly, could only observe its effects from what its instruments could detect. But the data was clear, unmistakable. The probe had found a wrinkle in the geometry of the universe, a scar from the first moment of creation, and it had taken 4 billion years and the end of civilization as anyone had known it to get there. Beat the humans on Europa read the data for weeks, not because the data was complicated though it was, but because they were deciding what it meant, what to do with the knowledge that the universe they lived in was not just old, but scarred, that the forces which had shaped everything, which had made hydrogen from quarks, stars from hydrogen carbon, from stars oceans from carbon life, from oceans and consciousness from life, had left marks, that the geometry of space-time bore the record of a moment before any of this existed. They decided it was enough, not that it solved anything, not that it told them where to go or how to survive what was coming, but enough the way certain kinds of knowledge are enough not because they fix anything, but because they complete something. The probe had spent 4 billion years asking the most expensive question in the history of the species. What else is there? And the answer, the complete, exhaustive, painstaking answer, was this: everything you could imagine, and several things you couldn't. Here is what the universe has made. It has made clouds of hydrogen 200 light-years across, drifting through the spiral arms of galaxies gradually gathering under their own gravity, until the center grows hot enough to ignite fusion and a star is born. It has made that process repeat again and again across hundreds of billions of galaxies, each galaxy containing hundreds of billions of stars, each star fusing hydrogen into helium and helium into carbon, building the periodic table element by element one, stellar death at a time. It has made moons with methane rain and oceans of liquid water buried under 100 kilometers of ice, and seas of ethane on worlds so cold that water is a mineral. It has made storms that have been raging for longer than civilization has existed. It has made a substance metallic hydrogen that behaves like nothing else in the universe and exists in quantities larger than all the terrestrial planets combined. It has made the void between stars so empty that a cubic centimeter of it contains fewer atoms than any vacuum we have ever produced in any laboratory. It has made that void not empty, but singing, threaded with magnetic fields, seeded with cosmic rays, humming with the low frequency vibration of gravitational waves from merging black holes a billion light-years away. It has made stars that steal the life of their companions, stars that pulse like lighthouses at 700 revolutions per second, stars that carry their own magnetic fields so intense that the fabric of the vacuum polarizes around them, stars so large that their deaths outshine the combined light of every other star in their galaxy, and stars so small and so patient that they will still be burning when the universe itself is entering its terminal decline. It has made singularities places where its own rules break down, where the equations that describe everything else yield nonsense, where gravity has won so completely that even the language of mathematics becomes uncertain. And it has made machines small, fragile machines built by small, fragile creatures on one small, fragile planet, sensitive enough to detect when two of those singularities collided 1.3 billion years ago, at a distance of 1.3 billion light-years, by measuring a change in the aeon length of a laser's path equal to 1/10,000th the width of a proton. It has made structures a billion light-years long, containing 100,000 galaxies. And it has made those structures hollow inside, empty their substance, given to the filaments and walls and nodes that define them, and woven through all of it, through the fabric of everything, so thin it is invisible and so massive it would crush a planet, wriggling at the speed of light through the void and through galaxies, and through the cores of neutron stars there may be the scars of the moment before any of this existed, the fossils of a universe that is gone, the wrinkles in the geometry of a space-time that was once far younger and far more violent than it is now. The universe did not make any of this for us. This point matters. It matters because one of the temptations at the end of a journey like this one is to feel chosen, to feel that the specificity of everything, the fact that the constants of physics have the exact values required to produce atoms, stars, planets, and consciousness implies intention, purpose, audience. It does not. The universe is not arranged for our benefit. It did not calibrate the strong nuclear force with human observers in mind. It did not position the Earth at precisely the right distance from the Sun, or give the planet precisely the right tilt, or time the formation of the Moon with any concern for what would eventually walk on the surface. These things happened. We benefited. The universe did not notice. And yet, we noticed. That is not a small thing. In the 14 billion years of the universe's existence, in the vast cold sweep of hydrogen and gravity and stellar evolution and galactic collision and void formation and the slow building of the cosmic web, we are the first thing we know of that looked around and wanted to understand what it was looking at, not merely to survive in it, not merely to avoid the dangers it presents or exploit the resources it offers, but to understand, to know, to build instruments sensitive enough to measure the width of a proton at the distance of a star, to look at a photograph of a ring of glowing plasma around a region of absolute darkness and recognize in it the confirmation of a theory written on a blackboard a century ago by a man who had never seen one, to find a star dying with a secret companion and name that companion her bracelet, To send a record into the dark, knowing it would never arrive anywhere we could follow, and put on it the sound of a mother kissing a child. This is a photograph taken by Voyager 1 on February 14, 1990. Voyager was more than 6 billion kilometers from Earth. At the request of Carl Sagan, the spacecraft turned its camera one last time toward the inner solar system and took a photograph. Earth appears in that photograph as a fraction of a single pixel, a pale blue dot, barely distinguishable from the background radiation, caught in a scattered ray of sunlight like a mote of dust in a beam of light through a window. Sagan wrote, "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world." He was writing about smallness. But the photograph is also evidence of something else, something that Sagan was perhaps too modest or too careful to state directly. We built the machine that took that photograph. We calculated the trajectory that brought it to that exact point in space. We asked the machine to turn around before it left our sight forever. We developed the image, we published it. We looked at it and we felt something. The pale blue dot is proof of our smallness. But it is also proof that smallness can build telescopes. That smallness can ask about its own size. That the universe, in the process of producing something trivially small and cosmically irrelevant, somehow also produced something that refuses to accept its own insignificance. We are the universe's one successful experiment in caring about itself. The universe made hydrogen, gravity made stars, stars made carbon, carbon made you, and you looked up, not because you had to, not because the universe required it, not because any force in nature, not gravity, not electromagnetism, not the strong nuclear force, not the weak had any opinion about whether you looked up or not. You looked up because you were curious, because 14 billion years of physics of stellar death and planetary formation and biological evolution had somehow produced a creature constitutionally incapable of looking at the night sky and not wanting to know what it was. A creature that builds instruments sensitive enough to feel a collision from a billion years ago. That listens for signals in the radio spectrum that no natural process could produce. That finds the companion star of a dying giant and names it after the bracelet on its wrist. That takes a photograph of itself from 6 billion kilometers away. That feels something looking at that photograph. The universe made stars and let them die. It made planets and let them burn. It made black holes that devour light itself and voids so empty they have no name for their own silence. But only once in 14 billion years of trying did it make something that looked up and wanted to know. That was us. That will always have been us.